All right. Today is November 17th, 2008. We're doing an oral history interview for the archives at the University of Alabama in Huntsville. Our guest today is Rick Chappell. Rick, we're delighted to have you here today.
Nice to be here.
I'm Charles Lundquist. For the record, we usually like to start out by letting the interviewee tell a little bit about their youth and how their career evolved and how they leaned getting into space.
I grew up in Montgomery, Alabama, and my folks were college professors. History, my father history, my mother English, and so I guess that's why I got interested in science. But I grew up in it started school in the late 40s, early 50s, and before there was a space program. And I tried to feel good about myself growing up by doing all the things we were supposed to do, like playing sports as best I could, which I couldn't do very well. So I was looking for things where I could feel good about myself, and as all of us do, I guess, throughout our lives. And it turned out that science and math felt pretty good, and I could do as well with that in school as my colleagues. And so in those years, I enjoyed it a lot. And then in 1957 with Sputnik, and then 1958 with Explorer 1, there was, of course, a great interest in America to stimulate the students and everybody really to be aware of and concerned about how well we did in science and math and engineering. And so my interest there, my abilities there, fortunately merged into what I heard America saying to me at that point in time. And so I began to think about the possibility of being connected to space exploration somehow I guess I was about 14 when Sputnik happened, so I was in middle school. And then so I took all the math and science I could through high school, and my senior year in high school, in May 25th, 1961, was when John Kennedy made his speech to the Congress about going to the moon. So, and that really was exciting, and I think sort of re-verified that I was on a track that fit what I was interested in, and that was going to mean something to my country if I could make a contribution. So I went to Vanderbilt, and I got I majored in physics and minored in math, and then I went to Rice University and got a PhD in space science. Finished in 1968. Went to Lockheed, so we were just about to land on the moon down the road from Houston up down at the Johnson Space Center. So being at Rice was an exciting time through the Gemini program. And then I went to Lockheed and worked in the research lab until 1968, and then I came here to Huntsville to work with you in the space science lab. And that was 1974, and that was to be involved in defining payloads, science payloads that might fly on the space shuttle in connection with Space Lab.
As I recall, you had a particular interest in the magnetosphere and all of the events that go on in it.
That's right. So when Explorer 1 measured the radiation belts, that was the first sort of measure of what was in space around the Earth. And when I went to Rice, by that time, Van Allen had used Geiger counters, which measured very high energy things. But by the time I got to Rice, there were little channeltron detectors that could measure ions and electrons at lower energies. And so we began studying. My PhD thesis had to do with measuring the particles that cause the aurora borealis and aurora australis, electrons principally. And then when I went to Lockheed, it's one of these things that happens in science every once in a while, where you're doing one thing and maybe the funding requires you to think about doing something else. And so I was studying the aurora and very interested in that, but the funds weren't there to continue the analysis of that data. But one of the Lockheed scientist Jerry Sharp had just launched a light ion mass spectrometer on a HOGO satellite, and so I was given the opportunity to work on that, which is what I've spent the rest of my life doing, studying the plasma, studying the ions that come out of the top of the ionosphere and fill up the Earth's magnetic field, and what all that means in terms of magnetospheric dynamics. So when I came to Marshall, you were kind enough to sort of let me pursue that research activity in addition to starting to look at payloads that might fly on the shuttle. So doing those two things in the Space Science Lab. And we were very fortunate to have support from the center to have the magnetospheric effort grow, and it became a branch at one point, and then I was lucky enough to get to lead that and then to merge that with the solar physics activity, and then we had a solar terrestrial division, and which I guess I did magnetospheric physics branch for about 10 years, and then the division for about 10 years, and then was asked to be associate director for science, which was the last 10 years.
During that period, or during the period when you were with the Space Science Lab, there were a number of experiments flown in space. Which of those catch your memory at this point?
Related to magnetospheric
Yeah,
physics?
the magnetosphere.
Well, we did. We built a little mass spectrometer that flew on the SCADA satellite, which was a DoD, principally a DoD satellite, and we built that almost entirely. We built it entirely at Marshall, and mostly in Space Science Lab with really great help from the other engineering labs. That was a nice experience for us, and then we built the retarding ion mass spectrometer for the Dynamics Explorer satellite. That was a wonderful instrument. Marshall built that. We built part of it, and the University of Texas at Dallas built part of it, and the University of Michigan built part of it. So it was a nice collaboration with Bill Hansen at the University of Texas at Dallas, and then Andy Nagy and George Kerrigan at the University of Michigan. That instrument worked wonderfully. I don't know, there's well over 100 papers that were written, and it measured the dynamics of the low energy plasma. So all of a sudden we could sit, it was a mass spectrometer, so we could tell the hydrogen from the helium from the oxygen, but we could see it moving, we could see its energy, and we began to understand that the ionosphere of the Earth was a huge supplier of the plasma that ends up in the magnetosphere. Still arguably, it's still a topic of great discussion. Maybe that the ionosphere is the entire source of what you find in the magnetosphere, with the other source, potential source, being the solar wind. And when I was going to school, and the Van Allen radiation belts had been found, and it was thought that everything came from the sun and got trapped somehow in the Earth's magnetic field. Maybe the other way around. The sun, the solar wind furnishes the energy which accelerates stuff, but a lot of the ions and electrons may come from the Earth itself, maybe even some of the particles that make the radiation belts start off.
So there's been a great deal of change in the understanding of the magnetosphere over your career.
A tremendous amount. It's to the point now, and then the second instrument that we did at Marshall was called, and this was when I was keeping up with football, I guess, we called it the TIDE instrument here in Alabama, the Thermal Ion Dynamics Experiment. And it flew, actually, the satellite was turned off this year after 30 years. So it took 30 years from the time the proposal was written until the instrument was built and flown and finished. And it's done. It was a very nice spectrometer and energy instrument that has contributed a lot to understanding principally the role that the Earth's particles play in populating the whole Earth space or magnetosphere. And that's really changed. I mean, it's a dramatic difference today over the way of the way that scientists think about how the magnetosphere is built, where the stuff comes from that makes it. So those experiments were very gratifying and I think successful, and there were an awful lot of people. We were very fortunate. There were lots of, through the support of the center and the interest that the community had with what we were doing, we had lots and lots of scientists who visited at Marshall, and many moved here, and many still live here. I think the group, the magnetosphere group, got to be where it was 25 or so scientists and support people, and it was one of those thrilling times when you have a whole lot of people who are good at a given area, and they interact with, there's this creativity coming up all the time because of their capabilities and their interactions with each other. So it was a very special time.
Well, as the shuttle came online, of course, you got involved in payloads for it. Can you tell us something of that?
In the beginning, I guess, when the shuttle was being built, Marshall became interested in playing a role in managing shuttle missions, particularly ones that might do science. And I think initially the Johnson Space Center was also. And so there were a couple of studies done. The Johnson Space Center did one that looked at using the shuttle to measure the atmosphere. And I think Bob Hudson was involved in that. And then Marshall did one through program development that Bill Roberts was instrumental in getting started, and it was called, I think it was PPEPL, Plasma Physics and Environmental Perturbation Laboratory. And so they did sort of a Phase A study with TRW. And I was still out living in California at that time when Bill got that started. And there was an interest in the center in that type of payload. And so, and I think the leadership felt that it would be good if there were. And because I had done research together with Fred Scarf at TRW, when Bill Roberts was talking with Fred about a possible project scientist that Marshall might get, Fred knew that I was from Alabama and suggested that Bill might talk to me, which he did. That was in 1973, and it was the center was approaching a major rift at the time, reduction in force, but I think there was an interest in trying to get that line of business, and so I came and visited and met Dr. Patron and met a lot of folks and talked about the possibility of coming here probably about this time of year, November probably 1973, and then was offered a job in February of 1974. And when I came back, there had been the reduction in force was already going, and several of the people who I had met in November weren't here anymore. So they had, there was a restructuring of everything, I guess, a very significant one. And so I was got to be in the Space Science Lab with you and started the research, and then we started looking to do a Phase B to follow on the PPEPL study. And I think NASA decided to combine the atmospheric things that the Johnson Center had started looking at together with the magnetospheric and plasma physics things. And so that became the acronym AMPS, Atmospheric, Magnetospheric, and Plasmas in Space Payload Possibility. And then and then Jack White joined the program development to manage that together with Bill. And I think Sam Morgan worked with us for a while, and then we did a Phase B with for AMPS, and they did a dual Phase B with Martin Marietta, it was at the time, and TRW as the two contractors. And then we formed a science working group, science study group, with scientists from all those disciplines, atmospheric, magnetospheric, plasma physics, and began to look at what we might do. And so those were my sort of principal areas of activity. I would be in the lab most of the time and be working on data from ATS, the ATS satellites and the IC satellites that colleagues had let us take responsibility for analyzing, and then working with PD to do these Phase B studies and to chair I guess I was the science studies of the project study scientist during Phase B. And we brought in lots of people that I had worked with in magnetospheric physics and atmospheric physics and began to look at what the shuttle might do. and that was from 1974 to 76. And then NASA went through one of its, we got to make sure we've got everything distributed between the centers correctly, studies. And there was a man named Todd Grew, you may remember that name, who was in the administrator's office, who was given the responsibility of shaking everything down and making sure NASA was running as efficiently as possible. And one of those decisions, which was very heartbreaking, was to take the AMPS project, which we had worked on for a couple of years, and send it to Goddard, since Goddard had done principally the science missions for NASA, not the human spaceflight ones, but many of the, most of the automated ones. And so it went there in 76. But it turned out, we said at the time, you know, Goddard's really not that interested in human spaceflight science, and so we were apprehensive about how that'll all take place. But Space Lab was coming along, which Marshall had responsibility for, and Jack Lee was managing, and they were jointly with the ESA, the European Space Agency. And so it was suggested that I switch over and become the mission scientist for Space Lab 1. And when the payload selection for that was done, lo and behold, many of the instruments that we had studied for AMPS
came back around.
It came back around, back to Marshall again, which was, and then as one anticipated, the Goddard activity just sort of melted away, and Marshall then was successful in getting management responsibility for Space Lab 1, Space Lab 2, which was astronomy and solar physics, Space Lab 3, which was microgravity, and on down the road. So,
as I remember it, Space Lab 1 was a very large and diverse collection of many, many experiments. You can probably expand on that a little bit.
There was, you know, two elements. One was the NASA ESA thing, where both agencies felt like they wanted to interest the science community in Europe and in the United States with shuttles. So there was an interest in getting as many of the, you know, leading scientists as possible involved, and in both Europe and America. And of course the Japanese proposed a very large electron accelerator, which was part of it. And so there was a generous selection from both sides of the ocean, and also there was an interest in showing that the shuttle could take care of a lot of different disciplines. So we did all of that too. We had those two dimensions of international, and then we did atmospheric physics, and we did astronomy, and we did astrophysics, and we did magnetospheric physics and space physics and material sciences and life sciences and probably Earth observations. It had everything on it, and that was exciting, but also challenging, because then all of that had to fit somehow. And so one of the challenges was to create a group, we ended up calling it an investigator working group of scientists who could work together to try to design the mission carefully enough that it would fit on the shuttle and fit in the space lab and allow everything to be done. The over-selection really made that almost impossible. And the other thing that was going on, of course, which NASA does so often because of being enthusiastic with getting on down the road, is that the shuttle was being developed at the same time, and the space lab was being developed at the same time, and the TDRS, the Tracking Data Relay Satellite System, was being developed at the same time. And all of those developments led to continuing changes in what the shuttle could do, and what the space lab could do, and the scientists were building the instruments at the same time. So we had this. There was a lot of rubberized requirement things going on. So we had to try to figure. There was a very interesting story in just figuring out how to do an investigator working group, and it reflects on the steps of the merger of science and manned spaceflight, which really manned spaceflight started as manned spaceflight, and with measurements being made particularly related to how to build a spacecraft and how to, have people live in space longer and that sort of thing. But less, most of the science was being done by automated satellites, so you had to try to bring those communities together. And Marshall played a very large, well, in Apollo, we had geologists, and because we were going to go to the moon, so there was some science, but it was also largely a human spaceflight driven activity to show that America could do that. And then with the Apollo science astronauts, it broadened a little bit. So Owen Garrett and Bob Parker and Bill Kerwin, and NASA, through the Johnson Center, selected scientist astronauts that were interested in life sciences and geology and space science and astrophysics and different things like that. It was beginning to merge, although it was still dominated by the human spaceflight considerations. And then Marshall played a huge role in Skylab, which then was almost entirely oriented toward doing science in orbit for a long period of time. And of course Owen flew on that. Bob Parker did not fly in Skylab, but had the role in the Skylab period of coordinating the science input to what was going to be done each day. But the scientists were in Skylab, had support groups from Marshall, people from Marshall were down there a lot, and but the scientists were not really allowed in the inner sanctum to interact with the crew. Their requirements were worked out, and then somebody else sent them up. And so, but Bob Parker had that experience. So when we tried to decide how to do the investigator working group, he was the first person that I talked to. He came up and spent a couple of days, and we just he went through the things he had done with Skylab, and then we talked about how we might do it with Space Lab and Shuttle that would allow even more interaction by the scientists with the crew. And then NASA gave the opportunity of choosing scientists to fly, which was a huge opportunity and a huge change. And so creating the investigator working group now, which has these 5 different disciplines, I don't know how many, I think it was 10 countries, so it was a lot of international. And then figuring out how, and it was about 60 investigators if we included everybody. We couldn't even get those in the same room. So we had to figure out how to divide it by disciplines and have representatives. One of the big experiments was a material sciences double rack, and it had, I think, 30 investigators. So we had to figure out how to select scientists who would represent everybody else, and how many would there be, and then how would the scientists select their payload specialists? That was sort of a clean sheet of paper to start with. The NASA astronaut activity had its standard way of doing things. They selected every 2 years and picked about 30 people. And they were doing, by that time, pilots and usually PhD level scientists who had some of the right experience to be connected to human spaceflight. And here we were with a clean sheet of paper on how we pick some scientists and do that in a way that the Johnson Space Center folks were comfortable with who we picked.
But who did you end up picking?
Well, so we picked, in the final analysis, Byron Lichtenberg, who was from MIT, PhD in life sciences. His backup was Mike Lampton, who was University of California, Berkeley, who was a space physicist and astrophysicist. And then Europe picked Gulf Maribold, who was a material scientist from Germany, and Vubo Akkels was backup from Holland, who was also a material scientist, fluid dynamics type. And we did that by having the working group pick 2 representatives from each of the disciplines. We called it the Payload Specialist Selection Group. We created an application form. We had probably 30 or 40 applications, and we went through those, and then we actually did an interview at Marshall and to pick the final for, and it was an international selection. And as you might imagine, the management on both sides of the ocean was, there was a continuing discussion between NASA management and ESA management about who gets to pick what. Mm-hmm. And there was a little bit of a wrestling between the NASA management and how much the scientists should be allowed to do in all of this process. So there was just a tremendous amount of discussion on all of that. And then we had to interface with the flight medicine people at the Johnson Space Center, who had to feel like the person that was selected would be able physically to do it, and psychologically. And there was the whole, are you the right stuff up here too? And,
so finally the shuttle launched with Space Lab 1 on board, and then another whole set of problems came about, I think.
Well, yeah. So we also had to figure out, one of the biggest things when you have too many experiments is who's going to get to run for how long.
How do you settle priorities?
That's
yes.
right. So we had to do that. So we had to do the timeline, a rough timeline, and then we also had to figure out how to modify the timeline as we went along. If an experiment had a problem, do you wait and try to fix it, or do you say no, we're not doing that?
Tell us about how that whole cycle worked during the operation.
Well, we created this Science Operations Planning Group, which was representatives, again, 2 representatives of each discipline, and they would go around and poll the experiments in their discipline, and they met every 12 hours. So as mission scientists, I would go in, we were on 12-hour shifts, and I'd go to the Science Operations Planning Group. They'd say, we need to change this, this, and this, and the planners would be in it, the Marshall planners, mission planners, and they would go off and work that for 12 hours. We'd be talking about a shift 12 hours away, and then I would go on shift and work that 12 hours, and then go to another science planning group that would look back at what they'd replanned and talk about what needed to be planned next, and then I would go and do a news conference to talk about what we just learned in the last 12 hours.
And you slept hardly at all.
Not much sleeping, but it was an exhilarating time. But the days were long for everybody. And then the European project scientists, we had because it was all of this reciprocity. So when I was on as a mission scientist, there was a European project scientist there, deputy. It was Heinz Ozer. And then Paul Craven was the assistant mission scientist, and then he'd come on the next 12 hours, and then there was a European project scientist, which was Carl Kanad. So we made sure that the management wanted to make sure that, these choices that might come up were being handled internationally correctly. So we had one of each thing there.
And always communications were a problem.
Yeah. And we couldn't, at that point, we couldn't talk directly to the crew. And what was done was that the backup payload specialist was the crew communicator regarding science. And so, since Ulf flew, Vubo was there as the backup, and Byron flew, and Mike Lambton was there. So we would, as mission scientists, we would look at what's going on, we'd listen to the problems, we'd go talk to the different investigators, and if it was something that had to be solved right then, we would make those decisions, and then either Vubo or Mike would talk with the payload specialists, and they'd make the changes. And then if it was a longer term problem, then we could go to the SOPG and get a broader guidance, and it was exhilarating. And by and large, the mission, I think, was very successful. Some of the instruments had problems, and like the electronic accelerator, ran for a little while, and then I think there was a washer loose in there someplace that found the high voltage after it floated around for a while and took the power supply out. So there were things like that, and there was the interaction with the media, who they were reasonably positive about the Space Lab flight, although they're always alert for difficulties that they might amplify. And so the press conferences were fun and challenging because it was an opportunity to present the really neat things that were happening, and dwell on the glitches that were coming here and then. I think that did pretty well. And then I was fortunate enough at the end of the mission to fly out to Edwards and watch the shuttle land with the space lab. And in fact, I think they lost 2 of the 5 flight computers in the last orbit before coming back down. And so they had to stay up an extra orbit and regroup with everything. Of course, there were 5 redundant computers, but 2 of them went out, and so they landed later than we thought. But and the crew was on the other crew members, other science crew members, Owen Garriott and Bob Parker were the mission specialists, and then John Young and Brewster Shaw were the commander and pilot. So it was a good mission. It was a triumph, and in terms of being able to figure out how to do all these things.
Yeah, I wanted to draw you out on all that for just that reason. You set the precedent for all the follow-on Space Lab missions. You showed them how to drive down that road.
We were. That was a very gratifying and challenging thing to go through. And lots and lots and lots of people involved, and the scientists generally had a good experience. I think it was an exhilarating experience for them, and unique for most of them. They'd never done anything involving manned spaceflight before. So it came out. I think it came out with sort of a happy bottom line. And of course in Spacelab 2, the follow-on missions did wonderfully. Different payload specialists, new payload specialists, and challenging things all the way along, which really led very much toward an understanding of how you might do a space station for a long term, how you might operate it, how you might involve the scientists. And at the end of Spacelab 1, there was because of the TDRS difficulty, you may recall the first TDRS communication satellite that was launched didn't get to orbit. Its apogee was in the right place, but its perigee was way too low. And so Goddard figured out that it could use the attitude control system and give it a little push once in orbit to raise the perigee until it got to geosynchronous orbit. And they did that. It was heroic. But the second one, TDRS then was not there, and so there was less air-to-ground data link. And so Spacelab 1 didn't get as much of the data as it would have liked to, and so it was decided to refly a number of the experiments. And I was fortunate to be selected to be a backup payload specialist for the reflight, what was originally called the reflight of Spacelab 1. That selection was in December of 1985, and then a month later a Challenger accident happened. And so NASA then needed to go back and find out what had happened and how to fix that, and that ended up slipping the reflight almost 7 years. It took about 4 years to redesign, to figure out the SRB problem and redesign it, and by then there were a whole lot of payloads that were backed up, and so it took 7 years before the reflight happened, and I got to function in the role of the alternate payload specialist and be in the operations center, which by that time then was at Marshall. In Spacelab 1, the Johnson Space Center had carved out a little space for us there next to Mission Control, sort of in the back rooms around Mission Control. And Marshall was very interested in having a full capability for the scientists and for the science operations, and so Marshall built the one here in Huntsville, which then for Atlas 1, which was in March of 1992, we operated from here. And the Mission Control Center interacted with the shuttle pilot commander, and then Marshall interacted with the science.
The Marshall facility, I guess, became the HOSC eventually.
Well, it became the POC.
Yeah.
It was in the HOSC building.
Yeah, it was the POC in the HOSC building.
Exactly. So the HOSC, I guess, had supported launches remotely.
Yeah,
and so in that same building then, it was a beautiful facility, the Payload Operation Control Center, which is now right next to where I guess it's called the Payload Operations Integration Center, maybe for space station. It's the Space Station Science Operations, which Marshall does too. And the figuring out how to, first of all, share resources, and then select payload specialists, and then how to figure out operations and how to replan operations. All of that was done in Space Lab ended up being very important for Space Station. Plus, then, the internet capabilities allowed a distributed operation where, because in Space Lab 1, all of the scientists came to Houston, and then in Space Lab in Atlas 1, all of the scientists came to Huntsville. And now in Space Station, most of the scientists can stay home and look at the data real time, interact with the operations center. And so that sequence of starting with a program which is almost all human spaceflight and not much science evolved to programs that were a good mixture of both. After the other thing that happened, I guess, somewhat regretfully, is that after the Challenger accident, it was decided, NASA decided, I think with a lot of input from the flight ops people in Houston, that you shouldn't fly payload specialists, that it's a dangerous business, and I'm not quite sure what all the rationale was, but that it should just be astronauts that fly, that are selected the way that we've always selected them. And so the payload specialist concept, which I think had worked pretty well, lasted through the Space Lab missions. And then when we got to the end of Space Lab, when we transitioned to Space Station, then it's all astronauts, many of whom are science background, but no longer kind of the science community picking its own representative. So,
For the historical record, let's just back up and get a few dates straight, and when you were attached to one organization and then went to the next one and so forth. We haven't got that.
I'm trying to see if I can remember.
We haven't got that on the record yet.
So,
we should do
so I visited in fall of '73. I was hired in February of '74, and I was in the Space Science Lab working for you. From '74, I think the magnetospheric branch was, I did that branch chief job for about 7 years, so that would have been '81. And then I was asked to lead this. There was an organization that created a solar terrestrial division, and I was the division chief there for also about 7 years. So that would have been '88. And then I was selected as the associate director for science in '88 and did that for 10 years. And then I retired from NASA in '98. I did two things there at the end. One was to work with Vice President Gore for a year in creating the GLOBE program. So I was still a NASA employee, sort of attached to the administrator's office and working for the Vice President. That was '94 to '95. And then I came back to Marshall, and then I did I can't think what IPA, I guess IPA, Intergovernmental Personnel Agreement. So I went to Vanderbilt, still a NASA employee, to do a study on the challenges of communicating science through the media to the public. And I did that at the First Amendment Center, which is part of, is connected to Vanderbilt. And we actually, Jim Hartz, who used to be the host of one of the hosts of the Today Show in the '70s, Jim Hartz and I did that study, and we wrote a little book about it called Worlds Apart. And then I decided to stay on at Vanderbilt to create a new major at Vanderbilt in science communication, which we now have. And there's students that are, it's an interdisciplinary major, and you can major in it in arts and science or engineering. And there have been 30 or 40 graduates at this point. And so I retired from NASA in '98, and I've been in Vanderbilt since then. So I'm in my 12th year at Vanderbilt, although the first 2 years I was still a NASA employee.
Let's go back to when you moved to 4200 as the associate director of the Center for Science. What were the problems you faced then?
I think the biggest challenge was to represent science as well as I could within the Marshall management, and it wasn't a problem as much as just something that I always wanted to do as well as I could, to have management decisions take into consideration what science needs. And so I tried to do that. I also tried to speak a lot, communicate science as well as I could. And one of the things which was very special, since Dr. Ernst Stuhlinger had been the first associate director for science, I think Dr. von Braun created that position, and Ernst was in that job. When I first started that, I asked Ernst if he would come and tell me the things he thought I should do, and we had many nice visits. And one of the things that he suggested was that when Dr. von Braun had been there, that he would occasionally bring world-class explorers in other disciplines to come to the center and talk about what they did. And he mentioned Dr. Christian Barnard, who had done heart transplants, I think, in South Africa. And Ernst suggested that we start to do that again. And so I tried to implement that idea in a thing that we created called the Von Braun Exploration Forum in memory of Dr. Von Braun, who unfortunately I never got to meet. He had gone to Washington by the time I came to NASA, and then he shortly thereafter became sick, and I know Dr. Stuhlinger used to go and visit with him, but I didn't get to meet him. But the Exploration Forum was to remember him, and then to have a person who was in exploration, different sorts of exploration, typically related to space, come and talk about the future in exploration. And then to add an additional element, we got entertainers who were also very interested in exploration, and particularly space exploration, people like John Denver, Lee Greenwood, to come and speak and entertain. So it was an attempt to bridge the space exploration that all of us are so involved in and dedicated to, bridge that to the public. That, of course, in Huntsville everybody knows about it, but knows about space exploration, but to link it to the public in ways that it would deepen their understanding and appreciation of it. And the forum, I guess it's still going, it has evolved a little bit in form, but I did that for 10 years, and we had some wonderful people come, and Dr. Stuhlinger was the first person to speak there. And remember Dr. Von Braun. I think Jack Smith spoke about, gave a talk, a speech that he had written after coming back from the moon that he gave to Congress, and then John Denver was there, sang a couple of very special songs, and talked about, in fact, global change, a subject that's in our consciousness today. So doing that was important, and then trying to encourage decisions at the center that would allow science to operate as successfully as possible.
Who were the center directors during your period you were there? You went through several of them.
Several, that's right. It started, it changed pretty rapidly. Jack Lee was the person who asked me to do that. And then, let's see, after Jack, I guess, was J.R. Thompson, and Jack was delightful to work for. J.R. was, I guess J.R. was center director. Jack was deputy director. Jack had been the one that interacted with me about doing that job. So it was J.R. Thompson, and then Jack, and then Porter Bridwell. And I think I overlapped with Wayne Littles just a little. So in those 10 years, and of course before JR had been Bill Lucas, who was Center Director when I came. Well, Rocco Patron was for just a short time when I came, and then he left and Bill Lucas became Center. So Bill Lucas was there probably the longest for the time that I was there, the longest as Center Director, and then Jack.
When you were up on the top floor of 4200 and the various center directors changed, how much did that change what you were doing?
They seemed all to appreciate the kind of things that we were trying to do, and I think and there was good steady support. Toward the end, I was trying to think. The Von Braun Forum had taken on a lot of elements, and I think toward the end, maybe Porter was not quite as convinced about how much effort we should put into it as the others had been. Although it never stopped. It was beginning to be looked at in a slightly different way, which then ultimately it did change after I left to be less of a production, I guess. More, it's a little bit less of a large scale event. We did. I had the good fortune of having Frank Six work with me, who was the University Affairs officer, and Frank is an extremely creative person, and he and I created several programs within university activities, which were a lot of fun to do, and that got shifted around a little bit just about the time that I left. I think that the University Affairs role was moved into another part of the center organization. Frank is still there and is in fact still connected to and contributing to the university programs. We created a program called JOVE, which stood for Joint Venture. We realized that particularly as the Earth observation system started, and there were going to be these massive amounts of data being taken about the Earth, and Space Telescope was launched, and AXAF was coming, and all of that there would be a chance to involve university people in the analysis of data who had not previously been able to be involved because their universities couldn't build the instruments, because it's a big investment for a university to get to the point where it can build space flight instruments. And knowing that there was going to be a lot of data coming, we worked out a way that professors at universities who were very interested in space but hadn't built any instruments could get access to the data and could get into analyzing the data. And that program worked really nicely. It fit nicely in with some of the other university programs that are already going on, where the professors would come in the summer and work with NASA people and then go back home. In this way, they could come in the summer and work, and then they'd go back home with a data line to a data set that they then understood, and they could start to make a contribution and involve students. That was a nice program, and that led, I think, ultimately to some adjustments within the university programs area that allowed the professors to do more. So that was another element of, I guess, what I was doing, kind of representing science to the public, which got me interested in the science communication thing, which led to the Vanderbilt thing. Go ahead. Doing the university things together with Frank and figuring out ways to expand that, doing the Von Braun Forum, and then sort of the conscience for science within the 9th floor management arena, and encouragement to management to make decisions that were going to keep science in mind. For example, in that time period, the tether was being developed, which was a real challenging engineering thing. And anytime you're trying to build something like that for the first time, the engineering management is extremely challenging and sometimes overbearing on the science you're trying to do with it once you get it built. And so I would be involved maybe occasionally in discussions on things like that to make sure we didn't throw the science out with the bathwater or whatever we were trying to.
Of course, another project that overlapped your whole time and everybody else's whole career was Gravity Probe B. Were you involved in any significant way in it?
I think not significantly, because I think Francis Everett is was so dominant in all of that it was almost like holding onto the end of the train.
Yeah.
And, so I was aware of it and certainly interested in it, but not. I think it was the way Francis wanted it to be, as you know, just as well as the money would allow. Now, that was a great, an amazing experiment. And then there was the redshift experiment too. There were two in gravitational physics.
How much of the early history of the space station overlapped with you?
We did an early transitional set of studies in which we thought we would take some of the instruments that had flown on the shuttle that needed to be up longer and put them on a free flyer that could dock with the shuttle, so that but would stay there, and so the shuttle could go up and point telescopes, do astronomy, do solar physics, do atmospheric physics interactively, and then leave it there where it would run. And those was called the Solar Terrestrial Observatory, and it was and program development worked on it, and Bill Roberts very much, and we that also was going on at the same time as folks were trying to figure out how to get power sources so that the shuttle could stay up longer, like the holding arrays up with the arm, or docking to something that had big solar arrays so you could stay longer. And so that was early on for space station. And then I guess the other connection to space station was that NASA was certainly interested in doing it. And after Space Age 1 happened, NASA saw that as an opportunity to encourage President Reagan to think about the space station. And so we were asked to go in the months following Space Age 1, to go talk to many audiences, several in Washington, about the success that had happened with Space Age 1 science and manned spaceflight, this experiment, and extrapolate that to space station. So it was very shortly after that, I think, that President Reagan announced that we would do a space station, which was at that time going to do a whole lot of things for not that much money, which is probably the way we almost always start. I don't know. And that led to where we are now, after many, many changes. Of course, the Gore, Chernomyrdin discussions that led to bringing the Russians in after the Soviet Union collapsed or reinvented itself or separated, the countries separated. And there were lots of Russian engineers available to do space things or other things that might not be as good for them that we didn't want them to work on, I guess, nuclear kinds of things. And so all of that was going on, and I think Space Age 1 played a real role in that, just because it showed that the manned spaceflight science thing was doable, and using the shuttle. And the shuttle would be the support vehicle for the space station. And I know, I guess originally, at least I've been told, that NASA's, after Apollo, that NASA's suggestion was this is the folklore anyway, but the NASA suggestion was a shuttle and a space station. That was the next thing to do. And that the shuttle would be two piloted vehicles. And so there was a price tag for that, and I think it was President Nixon at the time said, well, what can you do for half? And half was the shuttle with two piloted sections, and then he said again, what can you do for half? And so we ended up with the shuttle with the tank and the SRBs, but always with an eye toward ultimately getting the station there, and which we've done, and to everybody's credit, it's a pretty amazing thing that's happening there. And the one that's way out there is, of course, humans landing on Mars. And I know there are a lot of people in Huntsville that walk around pretty nearly every day thinking about how we're going to do that. And I'm really hopeful America will do that. It's the thing we should do. And it's the thing we can do for an amount of money which is, in the grand scale of things, not that much money.
Moving on to your Vanderbilt activities, can you say more about how this communication activity evolved and grew and prospered?
We in doing the study, Jim Hartz and I, we did a survey, a very extensive survey of scientists on the one hand and journalists, both writers and editors, the representation of the full media community, and asked why is it, in a series of questions, why is it so difficult to communicate science effectively to the public? And one thing that came out of that was that there are very few people who are bridge people who understand science and can write well or can explain science without its jargon. And so it became obvious to us that one solution would be to train undergraduates to do that. And there are lots of journalism schools, but very few have a linkage to science students. There are people decide on journalism at the beginning, and it's what they do. And so we thought and the journalism schools have been around a long time and have a fixed way in the way they do business. And so it seemed to us it would be difficult to start to change that. And so we thought, well, we'll just start from scratch within arts and sciences or engineering or wherever you want to place it, not in journalism. And Vanderbilt doesn't have a journalism school, so we didn't have to cross that bridge. And so we set out we brought together a committee of faculty people that represented all of the sciences, English, political science, history, the science education side, and asked them what collection of courses would be right for students to take to end up being well versed in science and engineering and the effective writing and communication studies was another one. And so we did that, and in the course of time, and as you know, like all larger organizations, universities don't create things overnight, and so that process of creating an interdisciplinary major took 5 years at Vanderbilt. But Vanderbilt had a way in which the students could define their own interdisciplinary major. It has some bounds on it, but you basically would decide what collection of subjects you wanted it to be interdisciplinary. And you can do that. And so we wrote a course map, and many students right away started individually selecting it and doing an interdisciplinary major. So it really started a couple of years after we had put it all together, and then it was ultimately worked through all of the faculty committees and have to approve new things, so that it became a major after 5 years. And now it has the order of 10 students a year that graduate, and they are finding, our original idea was that it would be valuable to have students like this because they could become science journalists. So they could write about science and engineering because they understood the people that do it and how it's done, the process, which most journalists don't. And that has happened, but also it turned out that there are all sorts of other careers that it works in. Public health, for example, where there are thousands of career opportunities, is about communicating medical science to the public and having them do the right thing.
Certainly.
So many of the kids did that. Several went to law school, environmental law and medical ethics law. 3 have gone to medical school. They wanted the communication skills to the doctor-patient. Wouldn't it be nice if you could understand what your doctor was saying?
Yeah, wouldn't it be?
That sort of thing. And some are in writing, some are science journalists. It's been a very successful experiment so far. And it seems that in schools, students often decide what they're going to major in talking to other students. And so in the beginning, when nobody's doing it, it takes some time for the word to get around, and that's what seems to be happening now. So, and the students also do internships. They work in a research lab for a semester, and then for a semester they write about that experience working with the science writer at Vanderbilt. And then in the summer between their junior and senior year, they work at NASA has hired, one has worked here at Marshall, one at the Johnson Space Center, one at the Kennedy Space Center. Many have gone to NIH in different elements of NIH. Some have gone to CNN. They enjoy having them in their science reporting things, and the American Heart Association. So all kinds of organizations that are at the boundary between science engineering and the public. So that's been a happy. It's been a happy thing. It's worked out well.
Very satisfying to do, I'm sure.
Very satisfying.
Well, as we draw toward the end of this, are there any final thoughts you'd like to share with the historians of the future, so to speak?
I think probably the one that comes to mind most clearly in today's environment is the role that NASA plays in fascinating students with the potential of doing something that nobody's ever done before related to science and engineering. And NASA people certainly understand that, and I think it's generally understood in the country, but not to the degree that I think it's needed. And I think America today, and for the past, really almost since Apollo, but most recently the last decade, roughly decade, has not appreciated the significance of America identifying challenges in exploration that it puts forth to its youth and says, come and be part of this. Like was done I mean, I was very lucky in my lifetime it was done, and it was done with respect to space exploration. And I think we need to keep doing space exploration for a lot of reasons, but particularly that reason, because it's those students who then become the creators of tomorrow's technology, which, I mean, every day now we recognize more significantly how the role technology plays in our economy. And there's a whole lot of things we can't make competitively anymore in America compared to other countries. And technology, if we can figure out how to do things that other people don't know how to do, we can sell them around the world. But in expanding on that, it's not just space exploration, which I think we need to do and which has proven itself to be successful in galvanizing the interests of students in science and engineering. But pick out a half a dozen areas and have the American leadership talk about them, like John Kennedy talked about going to the moon. Talk about alternate energy sources. Talk about nanotechnology. Talk about understanding global change as things that America is committed to doing, and the students hear that. They tend to do the things we as a nation represent to them to be important, and the media thing is one element of the challenge. We tell them a whole lot of things that appear to be important through the media that are not about exploration. And so I would hope that our country renews its realization that commitments to grand challenges, a number of grand challenges, in the words that we say and the way we support them, will make a huge difference in the future of the country, because it'll bring us tomorrow's explorers. And right now, tomorrow's potential explorers are not hearing that message, and so they often go and do other things. They're talented and they go and do other things. So my lifetime has in which I've been very lucky to have that happen, has shown me how significantly what America says to its youth, how significant that is if it identifies things that are incredibly exciting, very challenging, and then backs them up with both words and resources, it changes what the country is about and what it is able to accomplish. I would also say that the career of and I often say this to young people, that the careers that we have been able to have as explorers are just an incredible way to spend your life. And it never has seemed like a job. It's an adventure. And so if you want to have a life in which it's not getting up to go to work, but it's getting up to
have fun.
Go have fun and experience today's adventure. And that's what you want to do. You want to be an explorer. So.
Well, very good. Maybe this is a good place to wrap it up. Thank you very much for joining us today.
Thanks to UAH for doing this too. I think it's wonderful that you're capturing the history of it and also capturing some of the spirit of the past several decades, and in some cases, like Dr. Steelinger, his life almost a century of amazing things. So thank you for the opportunity.